Welcome to Lecture 25a, the camera. We're going to be describing the camera and its parts, and you're going to be able to define and calculate f-stop, exposure time, and image size. Okay, a camera is a lot like your eyes. In fact, it has all the same parts as your eyes, and they have pretty much the same function. Camera consists of a lens which focuses the incoming light and produces a real image. All but the cheapest cameras have compound lenses composed of multiple thin lenses. Now, your eye does too. Your eye actually has the cornea and your lens. The aperture, which controls the amount of incoming light and the exposure. In a cheap camera, like the kind you would, the old disposable kind of cameras, that would be a fixed size. It is variable in the more expensive camera. And this is the same thing as your iris in your eye. A detector which records the image, that would of course be the retina in your eye. In the old-fashioned cameras, this would be film. In a digital camera, this would be a CCD, and we'll explain later what that is. It's an electronic device. A light-proof enclosure, otherwise known as the camera body, keeps stray light out of the camera and provides support and alignment for the parts, sort of like your eyeball is. Now, a camera takes a picture by using a lens to form a real inverted image on a light-sensitive detector in a light-tight box. We can model a combination lens as a single lens with an effective focal length, usually simply called the focal length. Lenses are actually marketed and designed and designated by focal length. A zoom lens changes the effective focal length of the lens by varying the spacing between the two lenses that are within the compound lens. Typically, that is a diverging lens and a converging lens. A typical digital camera has an effective focal length that varies between 6 millimeters and 18 millimeters for a 3x zoom. Where does this number come from? Take the 18, divide it by the 6. Make sure these are in the same units. Okay, now a camera lens is actually a combination lens. Your eye is too. You have a lens and a cornea. The camera must carry out two important functions: focus the image on the detector and control the exposure. And that's the same thing your eyes do. Lenses focus the light, and cameras are focused by moving the lens forward or backward until the image is well focused on the detector. Now that's a little different than what it is in the eye. The lens itself actually changes its shape. In a camera, they just change the difference between the two lenses, okay, that make up the camera lens. Now, most cameras, the modern ones, do this automatically, but older ones require manual focusing. Most modern cameras use compound lenses made up of two or more simple thin lenses. Now, why do you use compound lenses? Well, all lenses have defects called aberrations. Compound lenses are used to correct such defects. It's sort of like what eyeglasses do for your eyes. Now, if you're wearing eyeglasses, you have 3 lenses, not just 2. When you have multiple lenses, you treat each lens separately. Do it in order of the light path. So the first lens that sees the light path, the one you want to analyze first, and then the second one. The image of the first lens acts as an object for the second lens, and you can make a sketch and be careful with distances and signs. Be very careful with distances and signs, and make absolutely sure you convert all the numbers into the same units. Below is a ray tracing diagram of a simple astronomical telescope. This also is a 2-lens system. If you go into Astronomy 111, we'll go into this in greater detail. The lens on a camera is usually a compound type, a combination of 2 or more single lenses. Consider a camera in which the light passes first through a diverging lens with a focal length of minus 120 millimeters, then a converging lens with a focal length f2 of 42 millimeters, and they are spaced 60 millimeters apart. A 10 centimeter tall object is 500 millimeters from the first lens. How would this lens be marketed? And lenses are marketed by their effective focal length. And you should be doing this before you come to class or before you review the lecture video. Now, the physics of this is a multiple thin lenses. And the formula I equals PF divided by P minus F, or F equals IP divided by I plus P. Now, these are 2 formulas that you can copy in your notes, and you won't have to rederive them. This is the power of doing things in symbols. Now, we know that F1 is minus 120 millimeters. Notice this minus sign. F2 is 42 millimeters. P1 is 500 millimeters. D is 60 millimeters. That's the distance between the lenses. And they want to know what is the effective focal length of the compound lens. First thing I do is check the signs. I got the signs right. Well, this is a diverging lens, so that one is negative. This one is a converging lens, so this one's positive. And this distance here is positive because it's on the side that the light's coming from into the lens. The other thing I do is check the units. All the units are the same. So I'm probably set up to go. You should do that sort of as a knee-jerk reaction to these things. When you write this stuff down, make sure you get everything correct. All the units are the same, and that you got all the signs correct. Okay, this is just a repeat of what we had before on the previous page. You handle the first lens the one that the light comes into first is the first lens. And you just write down what it is. I1 equals P1 F1 divided by P1 minus F1. And we have everything set up. We've got all the signs correct. All the units are correct. Turns out that I1 is 96.77 millimeters. Now notice the minus sign. Remember the sign convention for lenses. If it's a minus sign, then it's on the same side as the light came from. So this means that this image here is on this side of that first lens. So it's on the left of the diverging lens, and that's right here. So now this image is the object for the second lens. And you need to know that object distance. And that is going to be this distance, which was that 60 millimeters they gave you in the problem statement, plus the distance we just found. We don't need that negative sign for this because we need this entire distance. So it's 60 plus 96.77 millimeters or 156.77 millimeters to the left of lens 2. Now we're going to ignore the first lens and we do the second lens. I2 equals P2F2 divided by P2 minus F2. And we use this distance here for P2. The rest of it's pretty much self-explanatory. We put the numbers in here, make sure all the units are correct, the signs are correct, and we find out that I2 is 57.37 millimeters. It's positive, so it's going to be on the side opposite of where the light came from. This is the lens sign convention. So this is 57.37 millimeters to the right of the converging lens number 2. To find the equivalent lens, we need to measure all distances to the midpoint of the combo lens, which is right here, right where the cursor is. And that happens to be 30 millimeters from each lens, from either lens. So it's right between the two lenses. The new distances to the object image are 500 plus 30 millimeters, because we're talking about the original thing here. So what we're doing is effectively replacing this with a single lens. So now the single lens is located right here, so we need this distance. So that's 530 millimeters. I is this distance. So that's the 57.37 we found a few minutes ago, plus the 30 millimeters. So that's 87.37 millimeters. So F equals IP divided by I plus P. So here's our 87.37 millimeters. Here's the P of 530, that's the new one. 87.37, that's the image, the new one. And the 530 millimeters. It's a 75 millimeter lens. If you wanted to buy this lens, you'd buy a 75 millimeter lens. The image would form on the film of the electronic detector, and it would be upside down, that is inverted, and real. Now, if it weren't real, it wouldn't work at all. Because remember, if you're going to put a detector here and film, you wouldn't be able to see a virtual image. So it has to be a real image. If you get something that isn't real, you've done something wrong. And most of the time it's inverted. So be careful with that. In the compound lens shown, the parallel light rays will be focused at a point A, closer to, B, the same distance from, C, further than the second lens, then would be light focused by the second lens acting alone. And the first lens is a diverging lens. What they're trying to do here is compare what it would be like, where is it going to focus? It's going to focus somewhere over to the right here. What is the comparison between these two lenses acting together as a compound lens versus this one acting by itself as a single lens? Where would it be focused over here? Okay, so what it's going to do is the diverging lens is going to diverge the light. So instead of coming to focus here, like it would have normally done without the diverging lens, it's going to move that focal point out over here. So it'll be further from. Okay, another example. Your digital camera lens with an effective focal length of 10 millimeters is focused on a distant landscape. Then you take a picture of a flower 20 centimeters away. Now be very careful, I see a units trap right there. How far and in what direction must the lens move to bring the landscape into focus? The physics of this is a compound lens model is a single thin lens. We're going to assume the lenses of the combination move as one when the camera is focused. So, knowns and unknowns. First thing you want to do is convert everything to the same units. It doesn't matter which one you use. I decided to use millimeters. So F equals 10 millimeters and P equals 20 millimeters. And they're asking, where's the image? Formula is I equals PF divided by the quantity P minus F. Now, the landscape, whenever you're talking about a landscape, that's usually infinity. Okay, if they mention landscape, the distance to the object then is probably infinity. So P1 equals infinity. When P1 is infinity, the light will focus at the focal length of the lens. So that immediately means that I1 is F, and that's 10 millimeters. And this will be the initial position of the lens, because guess what? That's where the film has to be. That's how far the film has to be behind the lens to get that to work. So we're going to call that the initial position of the lens. The flower will focus when the lens is at I2 equals 200 millimeters times the focal length of 10 millimeters divided by 200 minus 10. And that ends up being 10.526 millimeters. The difference between the 10 and the 10.526, you would have to move that lens 0.526 millimeters further from the detector of the film. By the way, whenever a lens is as close as possible to the film, it's focused on something at infinity. So when the effective distance between the lens and the film is as small as it can be, the lens is being focused at infinity. So it's probably looking at a landscape. When cameras focus on objects that are more than 10 focal lengths away, roughly p equals 20 centimeters for a typical digital camera, the object is essentially at infinity and I is approximately equal to f. The lateral magnification of the image is m equals minus I over p, and of course if I is f, it becomes approximately equal to minus f over p. Now the magnification is much less than 1 because p is much greater than f. So the image on the detector is much smaller than the object itself, and that's a good thing. Otherwise, the camera would have to be huge. You'd have to have, you'd have to have camera the size of a person to take a picture of somebody. More important, the size of the image is directly proportional to the focal length of the lens. Now, zoom lenses are compound lenses and work by changing the distance between the individual lenses. A lens that can vary from f-min of 6 millimeters to f-max of 18 millimeters. That's a factor of 3 times in focal length, image size, and magnification. It's a 3 times zoom lens. And you can tell that by just taking the minimum, okay, and dividing it into the maximum. That's where the 3 comes from. Now, cameras must also control the amount of light that reaches the detector. If there's too little light, this is called underexposure, and the picture is too dark. If it's too much light, this is called overexposure, and the picture is too light and washed out, and you lose the detail. To do this, they control the size of the aperture and the length of time the detector is exposed. The amount of light passing through a lens is controlled by an adjustable aperture. That's the next slide. The exposure time is controlled by the shutter. That's a slide after the next slide. Getting the proper exposure is a balancing act between shutter speed and aperture. So we want to control the exposure, which is the amount of light. The amount of light passing through the lens is controlled by an adjustable aperture. It's like the iris in your eye. And this is shown in the photographs. You can see here is more open than here. The aperture sets the effective diameter d of the lens. So this little thing here would be the diameter of the lens versus that. The light gathering ability of a lens is specified by its f number, defined as the f number is f, which is the focal length, divided by d. Notice that the f number is written in 2 ways. Traditionally as f/number, such as f/4, is otherwise known as just f4. This is not a division, and the number is not the diameter or focal length of the lens. It's related to it, but it's not the diameter or focal length of the lens. Or the newer version of this is written as capital F4, but they're both just say F4. The full area of the lens is used when the aperture is fully open, but a stop-down aperture allows the light to pass only through the central portion of the lens. This would be definitely stopped down. All that's going on here is they've closed this aperture down. Now, the exposure time is also known as the shutter speed. That's controlled by, guess what, the shutter. In an old-fashioned mechanical camera, a spring-loaded mechanical shutter would literally open and close to control the time the film would be exposed to light. What it would do is it would just block out the light coming in from the lens so it didn't reach the film. And when you needed it opened up, let the light reach the film for a certain amount of time, and then it would shut again. In modern digital camera, the detector is an electronic device that can be turned on and off. That's much easier and much more reliable than having a mechanical shutter. Turned on when they want it to be exposed, and then when they want the exposure to stop, they turn it off. The exposure of the amount of light is directly proportional to the exposure time, which makes sense. The typical exposure time ranges from 1/1000th of a second or less for a very sunny, bright scene to 1/30th of a second or less for very dimly lit indoor scenes. For astronomical photographs, the exposure time can be weeks, and the mirrors, which take the place of lenses because lenses are too heavy at these sizes, can be many meters across. The light is so dim that individual photons are counted up one by one to make the image. Light intensity is actually proportional to the area of the aperture, and of course that means it's proportional to d squared, where d is the diameter of the iris. More light comes in through a larger iris, a larger aperture, and it's proportional to diameter squared. Light intensity is proportional to 1 over the area of the image, or proportional to 1 over the f squared. And this is from the size of the image is proportional to 1 over f, and the area of the image is proportional to the size of the image squared. So the light falling on the detector is more intense if it's focused onto a smaller area. The light intensity on the detector is related to the lens's f number by intensity is proportional to d squared over f squared, and that equals a 1 over the f number squared. The exposure depends upon the intensity I and the duration controlled by the shutter speed, delta T shutter. So exposure is the intensity times delta T shutter. Now, proper exposure is a balancing act between the aperture and the shutter speed. For example, faster shutter speed results in less image blur if you're trying to photograph something that's fast moving, but you may need to open the iris further to compensate for the shorter exposure time. We want to control the exposure. So focal length and f-number information is stamped on a camera lens. For example, a camera lens might read 58-23.2 millimeters, 1 to 2.6 to 5.5. The first numbers are the range of the focal lengths, and the second numbers show that the minimum f-number ranges from f2.6, or this is for this one, the 5.8 millimeter focal length, to f5.5 for the 23.2 millimeter focal length. Now, the f numbers can, of course, be written in two ways, the f/4, which is traditional, and the new one, capital F4. F8 will be written as f/8 or f8. That's not a divisor, that's a slash. Warning, the f number is not a division. The f in the f number is not the focal length. It's related to the focal length. Okay, digital cameras sometimes call the f number the aperture value. Oh, goody, something new. Setting the camera to any mode except automatic will display the shutter speed and the f number. Might say 125 f5.6. This means the detector will be recording for 1/125th of a second or 0.008 seconds, and an f over d of 5.6, where f is the focal length and d is the aperture. And in an automatic camera, the iris would be adjusted automatically. If the focal length is f equals 10 millimeters, the diameter of the iris will be f divided by the f number. So that would be 1.8 millimeters. So it's 10 millimeters divided by 5.6. Again, be careful with this. F number is not a division, and it's not the focal length. If the f number in a camera lens is doubled from, say, f4 to f8, what does that do to the diameter of the lens aperture? It's going to be halved. The f number is f divided by d, and if you double the f number here, the focal length is, of course, fixed. You're going to have to also have this. For a race, a photographer finds that she can make a perfectly exposed photo of the track while using a shutter speed of 1/250 seconds, that's 0.004 seconds, and a lens speeding of f8. To freeze the sprinters as they go past, she plans to use a shutter speed of 1/1000th of a second. To what f number must she set her lens? Okay, write everything down. The physics is a camera, exposure times, f numbers, and shutter speeds. We know the f1 number, that's an f8. We know the t1 is 0.004 seconds, t2 is 1/1000th second. The f number is what we need to know. Formula is I is proportional to 1 over f number squared. Exposure is I times the shutter speed. The algebraic solution, I1 t1 equals I2 t2. We drop the delta because, frankly, it's a pain in the butt. Okay, t1 over the first f number squared equals t2 over the second f number squared. The second f number equals the first f number times the square root of t2 over t1. We're ready to plug everything in. We can use f8 for the first one. That's the first f number. Here is t2, t1, the square root. Okay, so it's going to be an f4. Notice that you can actually use this in math if you're careful. As the shutter speed increases, the f number must be decreased. A camera gives a proper exposure of a scene when set to a shutter speed of 1/1000th of a second and f number of f16. The photographer wants to change the shutter speed to 1/250th of a second. To maintain proper exposure, she should also change the f number to, and here is a hint here, second f number equals the first f number times the square root of t2 over t1. Okay, if we apply the hint, write down everything we know. We know t1 is 0.001 seconds, t2 is 0.004 seconds, the first f number is f16, so the second f number is going to be the first f number times the square root of t2 over t1. So it'll be 16 times the square root of 0.004 divided by 0.001. So you'd need an f32. Now, I promised to tell you what was going on inside your camera or your cell phone camera. This is the detector. This is what takes the place of old-fashioned chemical film. So what is here is a top picture of this is a CCD. That is called a charge-coupled device. It's a chip containing many millions of tiny electronic detectors called pixels. And you wonder where the term pixel came from. This takes the place of old-fashioned film, which used photochemical reactions to record images on special paper, plastic, or glass. When light hits a detector, a charge is generated in the pixel in proportional to the light intensity, and it's stored there. After the exposure is over, the charge levels are read out, digitized, and stored in the memory of the camera for later retrieval. To record color information, Different pixels are covered by red, green, or blue filters. You can see that here, red, green, or blue. The pixels are so small that the picture looks smooth even after some enlargement. But if you over-enlarge it, you can end up revealing the individual pixels. And these are these little squares here. Now, this is the reason why good cameras have a lot of pixels that are very, very tiny. Also, where did this come from? This was developed for the space program. It was developed for the military. Astronomers have been using these since the 90s. So you wonder where your cell phone camera comes from, why this wonderful stuff that we have where anybody can take pictures and films and all kinds of stuff like that. Where did YouTube come from? The internet, all that came from the space program and the military. So you got to thank them for that. Thank you.